Okay, now so it brings us to the second property of rotations. It's a measurement of how hard things will rotate. And we can finally answer of the three shaped objects, let's say they have the same mass and the same, even the same radius, whether it's a sphere, a ring, or let's say a solid disk like that. I think I made a thick ring, but let's make it so thick that it's just a solid disk. Okay, and which one will race to the bottom and see if your intuition is correct and see if your guess is correct. Okay, so how are we going to analyze that? We need to see how easy things are to rotate. Okay, now there's a way to prove some of these formulas, but I'm going to defer that and just show you and just tell you some of the formulas first, so you can get a feel of them before we show you the proof of where they come from. Okay, so let's have the definition first. Just a quick reminder is, remember, moment of inertia is not inertia. It is a type of inertia, but when people say inertia, they mean linear inertia usually. And if you moment of inertia is rotational inertia. All right, so it's a measure of an object's rotational inertia. Okay, or rotational inertia just means it's resistance to motion, but resistance to a specific type of motion, to rotational motion. It's just like inertia or linear inertia is resistance to linear motion, moment of inertia. It's resistance to rotation motion. So roughly speaking, right? So this is the formal definition, but roughly speaking is, so let's just put it in quotes, right? How easy or difficult it is to rotate the object. So, right, in colloquial language, right, in everyday English, that's what moment of inertia is, and it's given by the symbol I, like that. Okay, so let's start with a point mass. How easy is it to rotate a mass, a point mass? Well, if it's a point and you just want to rotate about its own axis, well, then it's trivial. It is point, you can't really rotate it. However, let's say you want to rotate about a different axis. So I'm rotating about this axis of rotation, and here I have a mass. All right, so I want to rotate around. I want to fix it with. Let's say you can connect this with a rod. All right, connect it with a rod, and there's a mass on the end. We'll approximate that as a point mass, but I'll draw it larger so you can actually see it. The rod is going to be massless. Mass of the rod, right? So assume you have a stick. At the end, you tie a rock to it, and you want to rotate it this way. Okay, how will the inertia or the moment of inertia, right? But just how much rotational inertia would there be? What will it depend on? Well, it'll probably so I want my rod to be massless so that I don't need any effort to rotate my rod. I'm just concerning about a single point mass first. If you think about it, later on, if I really want to care about also the inertia of the rotational inertia of the rod is just made out of a lot of point mass, right? And you can deal with that separately. So we'll deal with simple case first. 1 point mass. How do I rotate that? Okay. So it will probably be proportional to its mass, first of all. Right, the heavier the point mass is, right? So we won't worry about the mass of the rod, right? It will be harder to, you'll feel more resistance in rotating it. The heavier, so it's probably proportional to that, and it will also probably proportional to the distance. We'll call it R, okay? And so this is how we, in fact, it's not actually just distance. Turns out if you move it 3 times further away, it's actually 9 times harder to rotate it, okay? I can't prove that yet, but we'll see that in a later video. So it's actually squared, okay? So this is the definition of moment of inertia for a point mass. Very important. If you're copying this, make sure you label a subscript, point mass, because if it's not a point mass, it's gonna be different, all right? For example, the moment of inertia for 2 point masses, what do? You actually just add them up, okay? But the answer will be 2 mr squared, right? So it's the moment of inertia of 1 point mass plus the moment of inertia of 1 point mass. Okay, so it will be mr squared plus mr squared. Okay, it's 2mr squared. So you see we have different formulas for different objects. Okay, we'll get to that. But just to complete the story over here, when you in an exam or when anyone asks you in physics to define something, you need to write out what the variable means, point mass, right? So this is the moment of inertia of a point mass. Okay, m is the point mass, the mass of the point mass. Okay, and r is what? Is the is the distance, or displacement technically, from the axis of rotation, to the point mass. Okay, so this is the axis of rotation. It's out of the board, like it's pointing out of the board, this axis, right? I'm rotating about this axis, and it's r is the it's the displacement from here to here, right? So you can put your origin anywhere, but this is the part. But technically, this is r square, so it's whenever you have square, you can't really square vectors. So whenever people write r square, that's the magnitude of it. So you either write let me correct myself. You either write r vector is displacement, and that will be understood as the distance, or without the vector and just write distance. That's also okay. Okay. So similar with a gmm over r squared in universal gravity, right? You have g capital M little m over r squared. Same thing. Whenever you see r squared, it's the distance. But don't just write distance, because distance from what to what? Distance has to be between 2 points, right? It's from the axis of rotation to the point mass, that way. Okay. The direction doesn't really matter in this case, but in general, the r vector is this way. Okay. From the, or usually we set this to the origin, so origin to here. Okay. And this is more correctly, it's the principal moment of inertia, because it's rotating about an axis, and that will just add, it's adding like a scalar. Yeah, okay. So if you have two objects, so if you have 2 point masses, okay, so like, and so if it's located over here, right, and this is m and this is m, how hard is it to rotate about the axis over here? If I want to rotate both of them at the same time, like this, imagine it's connected by a very light-weighted rod, or it's very light compared to these two. These two are very heavy, so all the rotational inertia, or the moment of inertia, is from the point masses. Well, it's easy. Just find the distance of this guy, distance of this guy. If they're the same distance, same mass, then the total moment of inertia in this case is just mr squared plus mr squared and 2mr squared, like that. Okay. Now we have clearly the configuration, like how the masses are distributed, is going to affect the amount of rotation. So let's say if I have an object, right? So it's very complicated, because if I have a random, like irregular object, it's made out of many point mass. So I need to add up all the, so if I want to rotate around this axis, I need to add up all the point masses that make up of this. All right. In fact, so if you approximate this and say, hey, let's keep it simple. Let's say it's mostly empty, and it's just a huge mass over here, a mass over here, a mass over here, a mass over here, and maybe a mass over here, but then also a huge mass over here. All right. So you approximate it to 1, 2, 3, 4, 5, 6, 6 discrete mass. Right. Then you can just calculate the moment of inertia for each point and add them up like this. So that's one way. So you see that if it's shaped differently, you will have a different I. Okay, so I depends on the shape. Okay, but also I depends also on the axis of rotation. Notice that, right? Because if I don't rotate about here and I decide to shift it and rotate about here, so this time I'm not rotating about sort of the center of this object, but rotate about here, so the whole thing sort of this spins around here, this spins around here, like that, right? The whole thing sort of spins about this point. Would it be easier or harder to rotate it? You would guess if it's instead of in the middle, it's somewhere over here, probably be harder, right? And why is that? Now you understand, because if you calculate the I, let's say you approximate with these 6 key points of the object, then this is the distance for everything, right? So your I total is going to be M1 R1 square, right? Call this 1, 2, 3, 4, 5, 6, like this, going around circle like that, right? So this is going to be R1 square plus M2, this is M2, R2 square, etc., right? But you see now more of the R's are longer. When in the middle, when this is in the middle, they're sort of all the same, but now only one is shorter, but more of the discrete points are further away from the center of rotation. So yes, this is shorter by shifting from here to here, but everything else is longer. So you have a larger moment of inertia. Can you see? This is now harder to rotate. Now I can simplify that a little bit more in saying, hey, instead of let's compare just 2 points over here, right? So you can make a separate example as well. To compare just these 2 points, what was the moment of inertia in this case? If I rotate about this axis, it is 2mr squared. Let me try rotate it about here. Okay, so this time this is half r, and this is 1.5 r, right? 3/2 r. Okay, so this time, be careful. What you plug in for the r is the distance from the axis of rotation to the point. Okay, so don't just blindly say if the diagram gives you is r over here, and the axis of rotation here, don't blindly just plug in, oh, that's r, that's the r. All right, you need to be able to understand that. That's why when in the definition, we need to specify what the symbols mean, because here r means the distance from the origin, but the question might be asking you the inertia, the moment of inertia to rotate it from here. Yeah, right. The moment of inertia to rotate from here, you will not plug in r. So that r is not the same as the r in the definition. The r in the definition is from the axis of rotation to the point. Okay. So you're gonna do I1 plus I2, and so I1 is m and 1/2 r squared, right? Plus R2, I2 is m, and the distance is this time 3/2 r squared. Let's see what we get. So here we get r squared over 4 plus m, and here I get 9r squared over 4. What do we get over here? So on top I have r squared, 9r squared, so I have 10r squared. So I've essentially, what's my factor in front? 10mr squared, right? So I have common factors mr squared, but here's 1/4, here's 9/4. So that adds up to 10/4, which is 5/2 mr squared. Okay, what's 5/2? Well, this is roughly 2, well, it's not roughly, it's exactly 2.5 mr squared. How much more difficult is it to rotate it, let's call this I prime, compared to rotate over here? This was 2 mr squared. Okay, now this makes sense, right? So the fact that this is just, if you rotate it here, it is harder to rotate than if you rotate it from here. So if you ever played with a stick and you try to rotate it in the center, it's slightly easier than trying to rotate it near the edge. In fact, what's the moment of inertia when you rotate it here? Okay, I'll let you calculate that. Yeah, so let's call this example B, right? Example C. I'll let you calculate that. How about rotate exactly on the edge? Okay, so I'll let you calculate that. The answer should be, I've done that before, so I know, or I've done enough of these problems, I can visualize it in my head. It's 4 mr squared. Okay, so you can double check that. Yeah, let's say edge. Okay, so it's actually twice as hard to rotate it from the edge than the center. Okay, so I think this fits with your intuition. You can double check, both double check my math and double check you understand the situation. And make sure you learn these two takeaways. It depends on the shape, and it depends on how things are distributed, and also from what axis of rotation you are from. Yeah. Okay. So these are all sorts of point mass. How about common objects? Okay. Let's address that in a separate video.